Okay, getting onto some more integration by substitution using trig integrals. So, our basic trig integrals are cos of x equals sine x, sine x equals negative cos x, and then sec squared x equals tan x. That's the one I was going over before. So to use trig identities, these are the trig identities that are provided on your formula sheet. There's also some more, but yeah, don't stress about remembering these. I think they're on like the last page of your formula sheet actually. So, as you can see here, we have all of these relationships between different sine and cos permutations. So what we use these for is to kind of simplify an integral that we have. For example, using this first one here, if we are asked to find the integral of 2 sine x cos x, this is obviously, we can't do this straight away, we have a product of two functions. However, we can just change this to the sine of 2x, and then we can integrate this just using some linear substitution, where our u is equal to 2x. So what we're just doing is we are trying to rearrange the integral that we've been given into a more like palatable or integratable form. So here are some other trig identities that are available. So again, for learning how to use these, what I would recommend is like making a list of circumstances in which to use all the different ones and then practicing. So what I did when I was in year 12 is I made a list of like, okay, well, if you have a product of like blah, 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 then use these identities. And look, like that's obviously not gonna, like, you know, memorizing kind of instructions isn't gonna get you anywhere in general, but it really helps for just kind of like recognizing the easier questions and not spending too much time on like actually figuring them out, because you can just look at them like, oh, like, you know, that's kind of like that thing that I have in my notes and I can just apply this, and it's really easy. But again, you do need to practice the harder questions and actually recognizing like the patterns between the identities for when you get to trickier questions, because I know, like personally, in the external that I did in 2021 for specialist, in the tech free section, the last question that we did was kind of this massive question. It wasn't on maybe it was on integration. I can't remember, but we had to use a lot of trig identities and just kind of the critical thinking that comes along with practicing a lot of complex questions for trig identities is the only thing that got me through that question. I think I ended up getting 100% actually, which I was very proud of for that question. But it was only because I practiced so many hard questions for trig identities and like was able to recognize the patterns between the two. You know, so obviously looking at like having the 2x and the x and the squared and the half, and then in these ones before similar things, and you know, knowing how to combine all of those to simplify something, because in some cases we're going to actually have to use more than one trig identity. Okay, so here we have some examples to have a go at. If you would like, pause the recording and have a go at these yourself. I'm just going to go through the solutions for these right away. So we're actually, I think, just going to go over the third example. just so we don't run out of time, because it is a little bit more complex. Again, if you wanted to practice the simple ones, pause the recording, but we'll just go through question 3. So, for this one here, we need to find the integral of sine squared 2x plus 1 dx. So obviously, the complicating factors in this question, or like the things that we want to get rid of, we want to get rid of the squared, because we can't integrate like sine squared. We want to get rid of that. And then we also want to get rid of the 2x plus 1 in the brackets. We want that to just be like a single thing. We don't want it to be a linear component. We want that to just be like x, really. So we want to get rid of the squared. We want to get rid of the 2x plus 1. We need to think of ways to do this. Firstly, we're going to have a look back at our trig identity. So I'll take you guys back to the previous slide. So typically when you're doing one of these questions, it kind of pays off to have your formula sheet in front of you, your QCEE one, and to like have a look through and recognize which ones you might be able to use. The one that stands out to me is this first one here, because we have a sine squared x, which is what we have in the question that we're asking. And this is then converted to a cos of 2x. So what this helps us do is get rid of that squared, because we don't want that squared there, right? That makes it way harder for us to integrate, or rather, it makes it impossible for us to integrate. We want to get rid of the squared, and this identity helps us do so. So let's apply this identity. So, do it over here. We want to find the integral of sine squared 2x plus 1. And our identity is equal to sine squared x a half 1 take cos 2x. So we're going to apply this identity. So what we have currently is sine squared 2x plus 1. So we're going to let this angle in the brackets be the same, and we're going to apply it. So our integral is going to be of a half 1 minus cos 2 outside of 2x plus 1. So as you can see here, we substituted our 2x plus 1 angle in for x. And now what we have is in our integral, instead of having a sine squared, we just have a plain old cos, which is a lot better. We have no squares. Now we can simplify this and see what else we can do to be able to integrate this. So we're going to have the integral of a half, take a half cos outside of 4x plus 1. So just expanding those brackets. Now, everything's looking better so far, but the one thing that we don't want is this 4x plus 1 in the brackets. This also makes it harder for us. And now you probably have learnt in methods how to integrate this, including the 4x plus 1, just by using the formulas that you've been taught, right? But because we are in Specialist, we're going to be using the actual method to do this, which is, of course, linear substitution, because we have a linear component within another function that we do not want. We want to get rid of her. So what we're going to do is we're going to do our linear substitution. And remember, the steps for this are to let u equal the linear component, 4x plus 1. We're going to derive this with respect to x, being our next step, leaving us with 4. Our next step is to isolate dx. And then our next step is to substitute this in to our original integral. So we're going to have a half, take a half outside of cos u multiplied by du on 4. So now we've gotten rid of that linear component within the cos, and now we can just integrate this with respect to u. So we are going to have a half u, take a half times the sine of u, and then this is all going to be divided by 4 because we have this quarter at the end. So now we need to simplify this, and of course our last step is to sub our linear component back in for u. So we are going to have 1 over 8 4x plus 1, take a half sine 4x plus 1 plus c. So this is of course going to leave us with 4, I'll just move it up here, 4 on 8, which is a half x. We're then going to have like a constant because we're going to have an 8 times 1. We can leave that out because of course the plus c is going to encompass the constant. We don't need to include that. And then we're going to have take 1/8 sine of 4x plus 1 plus c. And that is our integral. Okay, so in this example here, as we went through, we needed to use our trig identities to get rid of the squared section. And then because we had a linear component left over, we then had to use linear substitution. So this is an example of a case where we have to use two different methods of integration for one question to come to our answer. This is kind of a base level example where we have to use multiple methods. If you kind of try to do some harder questions from your textbook, and we'll also get to some harder examples in this lecture, but if you try to do some harder questions from your textbook, you will come across some that are like absolutely mental, and you have to use like 5 different types of integration to come to your answer. So take this as kind of like a base level example. Okay. Here is a more complex example. And this is where we are finding the definite integral instead of the indefinite integral as we've been doing thus far. And we need to use a substitution x equals 2 sine theta. So, as you can see here, what we have, and before we actually get into the rest of this question, I'll just explain the thinking behind this example, because I think that's the hardest part of this. The thinking behind this question is that we have this 4 take x squared in a surd, right? So we can't integrate this straight up. We can't integrate it straight up. Your next thought might then be, oh, nonlinear substitution, we have a nonlinear component, we'll just chuck it in. However, nonlinear substitution, if you remember from, a few minutes ago maybe, only works when we have like two functions together. If we have like a product or a quotient or something of that kind, because then the derivative of our u is going to cancel out, and we're going to be left with no leftover x's. But in this case, we only have one function, so we can't use nonlinear substitution. And I know if this is your first introduction to integration, this kind of might seem like a lot. But if you do want to practice that out and try using nonlinear substitution and write that out, that might also help you understand why we can't use it. Again, it's because we don't have those two separate functions. So the derivative of 4 take x squared isn't going to have anything to like cancel out with. So we're going to be left with this extra x. So following this logic, we know that we can't use nonlinear substitution. But we know we do have to do something to simplify what's under these brackets. And this is an example of when we can use trig identities, not just to simplify a trig function to begin with, but actually to do some substitution. And again, if this substitution does not seem immediately obvious to you, I do not blame you. This is very tricky. I hope, though, that the explanation of why we got to this, or how this is the only option, makes sense. So, the reason that we're choosing to substitute kind of using trig is because we have this surd, and when we're using our trig identities, we often have a lot of trig identities that have a squared trig component and like a constant number. So what we're thinking with this substitution, and we'll get into what actual identity is used in a bit, but what we're actually thinking with the substitution is if we can put this in here, we might be able to find a identity that like leaves this with something like cos theta squared or whatever under the surd. And if we do that, then we can cancel the surd out, which makes our integration a lot easier. So that is where that came from. We're just recognizing that with the trig identities, we have like a lot of, a squared trig function plus a real constant number. And hopefully we can utilize that if we have a squared trig function under here to kind of cancel out the surd, because we don't really have any other option as of yet available to us. Okay. Now that the thinking behind this question is explained, let's get into the actual purpose of this example, past explaining substitution and trig identities and giving a more complex example. And that is to actually explain how we can use substitution with definite integrals as opposed to indefinite integrals, which is what we've been doing so far. So, if we are ever using substitution in a definite integral, we need to change the bounds of the integral. And we do this by setting x to be equal to each of the values of the original bounds, then solving for theta. So, we'll get into how this is done on the next slide. And just as a quick note as well, there is an easier way of doing this question, which you might have recognized if you've gotten a little bit farther into integration, and particularly all the different functions and trig functions that we can integrate. But we're going to have a go using substitution just because it's a good exercise. Okay. So, over here, we have the solution for this question. So, we have x equal to 2 sine theta, and then of course we are going to differentiate x with respect to theta to get dx d theta. So this is, of course, the second step of substitution, where we let our substitution be equal to a particular letter. Then we differentiate that and we isolate the dx. Now, we need to change the bounds. And this is a step that's important when we're getting into definite integrals as opposed to indefinite integrals where we don't have bounds. So as we said in the slide beforehand, we need to let the previous bounds be equal to our substitution. So our substitution was 2 sine theta. Our previous bounds were 2 and 0. So we're going to let 2 sine theta equals 0 and 2 sine theta equal 2. And this gives us that theta is equal to 0 and pi on 2. And this you could get just, of course, by using your table of values or your special triangles. So, again, when we have a definite integral and we're using substitution, we need to change the bounds by letting our substitution equal to the bounds. So, I'm just cracking my back. Excuse me. So, once we've changed the bounds, we now need to apply this to the integral. So, we've put our new bounds into the integral, and then we've subbed in our substitution. So, of course, we have our 2 cos theta d theta, which is our sub in for dx. So we have this, and this is coming down here. And now what we did is we let x equal 2 sine theta, and then we substituted this in our surd. So, as you can see in our previous slide over here, we just substituted it in, and then this can simplify to cos squared theta. So, what we did up here is we simply subbed it in and then factorized out the 4. Then from here into our next step, we recognized the Pythagorean identity. So, remember, sine squared theta plus cos squared theta equals 1. So, of course, we just rearrange this to get cos squared theta equals 1, take sine squared theta, and this is, of course, what we could substitute in here. Moving on from here, we removed this square root, which, of course, left us with cos theta multiplied then by this section here, which is 2 cos theta d theta, which once again left us with another cos squared theta, which is annoying, but it's better than what we had before. And then, of course, we could take the 4 out the front. So, from here, we still don't want the squared in that cos theta. We need to get rid of the squared, and what we can do is use one of our trig identities to get it down to a cos with a power 1 instead of a power 2. So, the identity that we used was this one here, which is the cos of 2x is equal to 2 cos squared x, take 1, And of course, then we could rearrange this to isolate cos squared x, which gives us a half cos 2x plus 1. So we substituted this in here. So of course the half took our 4 down to a 2, divided by 2. But it left us with what we wanted down here, which is 1 plus cos 2 theta. And now we can integrate this easily just using our regular linear substitution. And we can just apply our definite integral rule. So we're going to keep the 2 out the front. We've obviously integrated, so integral of 1 with respect to theta is theta. The integral of cos 2 theta is going to be sine 2 theta divided by 2. You could use linear substitution here, but of course we just use like the regular rule, which is that if you have, this is what you would have learned in methods as well, is if you have like the cos of ax plus b, then the integral is going to be equal to 1 on a sine ax plus b. And that's what you would have learned in methods. Okay, so we just applied that, and then we applied our regular definite integral with our limits. We subbed in our limits, and this gave us an answer of pi. So, as you can see here, the only difference with definite integrals is that we need to sub in our limits and change them a little bit to correlate to the substitution that we are using. But other than that, not much has changed. It's pretty straightforward. So, now we are going to get onto the derivatives and integrals of arc sine, arc cos, and arc tan. So, we don't go through these in methods at all, but remember the arc sine, arc cos, and arc tan is like the inverse. And by inverse, I don't mean, I do not mean like 1 over sine. I don't mean that. What I mean is like the inverse. So when you are finding the angle. So if you have, sine of theta equals 0.5, theta is going to be the inverse sine of 0.5, right? This is what we're talking about when we're talking about the inverse, and this is of course also written as arc sine. So, again, we're talking about arc. We're not talking about like 1 over, like we did over here. We're talking about the inverse, which is like where you're trying to use the value to find the angle. Okay. So, these ones are on your formula sheet, and they just essentially tell us that like the derivative of inverse sine is equal to 1 on root 1 take x squared, and then conversely, of course, the integral of this is going to be equal to the inverse of sine. So this is how we use it in applications with integration. As a hint, to solve these types of integrals, if the integral is in the form a on a squared plus x squared dx, use x equal a tan theta. And if the integral is in the form 1 over root a squared take x squared, use x equals a sine theta. So yeah, these are just like some basic tips for integrating with these trig functions. We're not going to get too deeply into it just because we want to get more so onto the different methods, not including integration. Not integration, sorry. Substitution. But these are just some general tips for actually applying these formulas. Okay,